let's proceed with the last talk of the session about semiconductor manufacturing processes and the related plasma reactor. So this is the outline of the talk. I will start with an overview and the main context for the simulation of the semiconductor manufacturing processes. Then we'll see also the simulation techniques for plasma reactors. And I have a couple of examples that I would like also to present you. Then thin film deposition, which is done via the so-called DC magnetron sputtering. And you will see also the famous JEC CCP reactor example. And I will also show you a VHF ICP reactor, and then we will conclude. So let's start with the motivation and the main context in this area. So first of all, the semiconductor industry is really a strong competitive market. You see, for instance, the worldwide sales in 2023 reached $520 billion, and it corresponds to a decrease of 8% compared to 2022. But the estimate forecast for 2024 is roughly $590 billion. And then you see that in this case, we should recover to 2022 with a slight increase of 4%. And there is a reason for that, because there is an increased demand for IoT, Internet of Things, and integrated circuits. And there are needs for automation, reduced product development timelines, and this requires an increased development and fabrication costs, and innovation and competitive developments has to be also performed in that regards. So the simulation tools at the fabrication process level can here help facing those challenges, and that's really challenging. The motivation and the context, there are three main parts here: physical and technological motivations. There are also economic reasons, and advanced etching processes, which needs also to address this by the simulation. Regarding the technological motivations, more and more the semiconductor components are getting smaller and smaller to address the applications related to micro and nano technologies, and there are requests on small feature size. And of course, as soon as we are going to miniaturize these components, there are also economic reasons. First of all, there is a global chip shortage since 2020, and then the mass productions needs to be optimized in order to really provide with something which is first accurate but efficient at the same time. And this requires advanced etching processes to address the new semiconductor technologies, such as larger size wafers, plasma reactor design challenges that we have to face with, plasma homogeneity control, and a better etching process quality that we need also to consider. Here you have the different processes which can also be addressed by the simulation. And regarding deposition, we can do DC RF sputtering. Regarding the etching process, you have here different kinds of etching process, such as wet chemical etching and physical abrasion, as well as dry plasma etching. And CST Studio Suite will be well suited for dry plasma etching process and the related plasma reactors. We can do also some doping with, for instance, the applications related to ion implantation. And since you've seen already that we are able to do the design of ion sources, and then we can then extract the ions and then guide them to a certain target and so on. This is the typical workflow that we would use for ion implantation, and a bit of lithography as well with e-beam lithography, which is, for instance, the picture that you can see here, something that we can try also to simulate. Regarding the etching process, so you have the wet etching process, which is a chemical process, and you have the dry etching process, which is a physical and a chemical process also at the same time. It can also be fully only physical. The wet etching process is really, as I said, a chemical process. This is not under the scope of CST Studio Suite, but here you see that it has an effect also on the way the process is done. So with the wet etching process, you have here an isotropic etching, whereas with the dry etching process, then you can address small feature size and you have an anisotropic etching process. CST is really in this category, where you can here consider a plasma exposure with a better control of the physical parameters. And then you can really perform the plasma simulations of the plasma reactors that you need also in this context. You have a better selectivity of the materials to be etched, defined by the mask. This is an accurate and reproducible and uniform profiles that you can also consider, and that's useful, as I said, for small feature size. Let's now have a look to the classification of the different etching processes. So you've seen that we have the chemical processes and the physical processes, and these are linked to the range of pressure that we need to address depending on the applications. So for the very low pressure applications, then we are in the area of the physical processes. So that means plasma exposure with low plasma densities, and this is here exactly what we would be able to simulate using our ESPIC solver. This is here the context of the simulations with CST. And whereas as soon as the pressure is increasing, when you have higher plasma densities, where you also need to take into account the chemical processes, then in this case, we need to think about something different. So regarding these applications, which is related to the process with the plasma exposure, then we can here use the simulation to perform the analysis of the plasma reactor. We can, for instance, explore new plasma reactor design. We can improve uniformity of ion density profiles. We can also couple our simulations to any thermal analysis to prevent damage that we might have also in this context. We can also explore the effect of using different types of gas, noble gases typically, in order to get rid of any chemical reactions such as argon, neon, etc. Pressure and external sources effects can also be taken into account and see how they affect also the plasma homogeneity. And we have a high fidelity modeling to predict and explain experimental results when we have no diagnostics to analyze what's going on in the plasma chamber. So plasma modeling, space charge dynamics interactions, transient effects, and so on can really fully be taken into account with our simulation tools. So let's have a look now to the simulation techniques for plasma reactors. You've seen already the slides that we have a microscopic behavior and a macroscopic behavior. So the plasma can be treated with considering the species that we have into the plasma, electrons and ions, and taking into account their interactions. Then we can perform the ionization of the neutral gas at a given pressure, consider the Monte Carlo collision also superimposed to the model, and then we can perform then the plasma and establish the plasma up to the plasma regime in order to extract the electron and ion density that we have into the plasma. With the macroscopic behavior, the plasma is treated as a bulk, and then we are using, in this case, CST Studio Suite, Microwave Studio. And we can here use whatever the time domain solver or the frequency domain solvers. We are going to use the Drude dispersion models or any kind of dispersion models which would characterize the plasma as a bulk. And if we need also to superimpose any magnetic field, then this can also be done with the electric gyrotropic dispersion models also available in the CST Studio Suite. Regarding the microscopic approach, you've seen that we have two dedicated solvers. So we have the particle in cell solvers and the electrostatic particle in cell. So the particle in cell algorithm is working as follows. This is a time domain kinetic approach, and it's a self-consistent approach. So you solve the Maxwell's equations. Then the Maxwell's equations is going to provide you with the E and H fields, which are then introduced into the equation of motion for the particles. And then here you can calculate directly the current density and the equations of continuity. And then at each time step, which is defined by the mesh grid, you will then modify locally the E and H fields that you will then reintroduce into the equation of motions, and so on. You will get the self-consistent analysis. We can here superimpose also the ionization feature, and this supports also the GPU in order to speed up your simulation. The difference with the electrostatic particle in cell solver is the following. This is also a time domain kinetic approach. You can see it also as a time tracking, where the tracking solver is a pure static solver. And the time step here is not limited by the mesh grid. And this is something that the user can enter manually. So how does it behave? So you have here the numerical solutions of the Poisson's equations in order to calculate an electrostatic solution. These electrostatic solutions allows us to calculate the E field, and the E field is going to push the particles. And this creates a certain charge deposition, which is then re-injected into the Poisson's equations to get a new solution for the E field, which is then push again the particles in order to get a full space charge dynamics, which is then computed with the ESP solver. The drawback, of course, with this method is that we neglect here high frequency electromagnetic waves effects. We don't compute here the induced H field, and there's no power also generated. So in other words, you don't have any current which is generated with this approach. We only consider the space charge dynamics. And the ionization features, together with the Monte Carlo collision models, are also then available. And part of the features that you have with the ESP is also supporting with the GPU. So let's now have a look to the microscopic approach, as I said. So then we can use the Drude dispersion model. So that's a bulk approach. You have here the plasma, which is treated as a load, and that's well suited for matching network optimization. You can use whatever the time domain solver or the frequency domain solvers, and then you can perform here a real cold plasma description with a 1D dispersion model that you can enter, which follows the equations, and the parameters of the equations are directly entered here into this dialog box. So then you can here enter the plasma frequency. You can also enter here the collision frequency, and if needed, you can superimpose also a biasostatic B field, and then use, in this case, the electric geotropic dispersion model. So let's have a look to a particular example. Here, I'm using the Drude dispersion model, the nonlinear Drude dispersion model. So how does that work? You've seen this part of the dialog box previously, and we can also enter the field breakdown and the plasma maintained frequency. So that means that here, if you use the time domain solver, which is available with this technique, as soon as you reach the breakdown E field, then you initiate a plasma with a certain plasma frequency. And the plasma is maintained over a certain electric field. And then as soon as you are below the electric field, which is defined here to maintain the plasma, then below you handle with the dielectric. And you can really perform this in the time domain. This is well suited for CCP-like reactors. And you can see here on the picture, you have a powered electrode of 100 volt at 13.56 megahertz. And with the grounded electrode, then you can nicely see how the plasma is distributed over the structure. Let's now analyze particular examples which is related to DC magnetron sputtering. So the workflow is the following. We have here the design of a plasma chamber. So then this can fully be designed, or you can even import your structures or link this to your CAD tools that you are commonly using, which would be whatever CATIA or SolidWorks. And then you can set here the external static sources definition. Then you see here on the picture, you have, for instance, the static magnetic field, which is then here perform with the focusing magnets that we have introduced. And we can then afterwards introduce the neutral gas into the computation domain. Here we are going to use the properties for argon. Then we are going to enter the ionization cross-section for argon, consider the elastic inelastic collisions with the Monte Carlo collision models, and we can parameterize the pressure in order to analyze what will be the plasma and the ion density profiles at the end of the simulation. Then we are computing here the simulations using the electrostatic particle in cell solver. The plasma formations and the space charge dynamics is then automatically computed. And then here you can then afterwards have an idea of the ion density profile, which then can be extracted out of the simulation. And then you can have this kind of figure. So the plasma reactor optimizations can also be performed. You can play on the pressure and on the different parameters, which might also be geometrical parameters. And then at the end, you have all the informations to compute the target erosion profile. And then you can do thin film deposition, and then you can then extract the efficiency of the whole device. So let's apply this on a particular example. So this is an example thanks to collaborations that we had in the past for a study between Tier Coatings and the Open University in the UK. And this is the structure. So you have here a target, you have here the plasma chamber, and you have the substrate. And the deposition will be performed here on the surface of the substrate. And you have here some cylindrical permanent magnets for computing here the static magnetic field. So here within the plasma chamber, which is filled with argon neutral gas, we are going to ionize the environment. Then we create electrons and ions. The electrons positively charged will be then moving to the target, which is then negatively charged. When hitting the targets, they will emit some atoms, the atoms made of the materials of the target, which is in this case could be aluminum, copper, or titanium. And then these atoms will then deposit everywhere and will participate to the deposition process. Here you see we have a target which is here fed with the voltage of minus 400 volt, and the thickness of the target is made from 1 to 3 millimeter. This is the type of results that we can extract out of the simulation. This is a real transient behavior. On the left-hand side, you have here the energy distribution of the species created into the device. Then we have here, you can see the electrons and the ions, which are then moving into the whole device. And you can see also the plasma expansion with the particle energy concentrations, which are then mainly concentrate close to the target, because this is where we would like to extract the atoms to be then afterwards deposited on the substrate. On the right-hand side, then you have here the charge that we compute here, the charge per cubic meter. And you can see that the plasma is mainly concentrate close to the target and expand also a little bit everywhere, but mainly concentrate on the target, where, of course, we need to extract the species for the deposition process. We can then extract such a plot, and we can perform the analysis and see this from the top, where we have the target surface. So you see here, if I'm applying here a curve in this area, and if I'm going to look inside, then you have this figure. Here you have the z-axis versus here the x dimension. So that means perpendicular to this plot that you have here on the right-hand side. Then you see that we can also see the erosion profile on the target. So this can be estimated by the simulation, and we can compare this also with the experiments. And by the way, you can nicely see also the ring of plasma, which is then generated hitting the target at the end of the process. When we compare this with the measurements, so you have the calculated results, which corresponds to the previous slide with the results, which has then been computed using directly the simulation. And you see that when comparing this with the measurements, we have a very good agreement, and here a very good prediction on how the target will be eroded during the process. And this also gives us some information about the lifetime of the plasma reactors that we will have to consider for our process. So very useful to use the simulation also in this context. I would like now to provide you with some information about the CCP plasma reactor, and you will see also how we can set the workflow for this type of application. So I've used here a well-known paper, which is a reference in this community coming from the GEC, the Gaseous Electronic Conference. And you have here in this paper a two-dimensional self-consistent RF frequency plasma simulations, and performed in 2D in 1995. And so this is a well-known plasma reactor, so that's good because we can then benchmark and reuse also this model for our own purposes. And at low pressures, the kinetic approach is here much more accurate than a fluid approach. Because in this case, we are not neglecting anything. We are really taking into account the real process that we have into the reactors. So because the process is really dominated by the collisions. So this is well suited for a kinetic approach using the ESPIC solvers with the Monte Carlo model. And then we can now try to perform these simulations no more in 2D, but in a full 3D model. And you will see that in a real 3D approach, we can capture some effects, some physical effects that we are not able necessarily to see also in 2D. So first of all, we have to set the problem, the numerical settings, and we are going to use here the argon neutral gas as the background gas. So you have this special dialog box where you can enter the name of the gas, the mass unit, the pressure range, the pressure that you're interested in, the temperature, and so on. So here the pressure is defined at 200 milliliter. We have a temperature of 300 Kelvin and a maintained discharge over 13.56 megahertz RF voltage. And then we can then introduce here the different cross sections that we need for the simulation. So we have the ionization cross-section, the excitation, and the elastic collisions. So these are the Monte Carlo collisions that we can enter. And you see here, you can also enter your own data if you have an effective gas that you would like to take into account, which is not necessarily tabulated somewhere. So here you see you have this kind of figure, which are then pretty well known also in this community. And we are going to use these plots to drive the ionization, the excitation, and the elastic collisions within the plasma environment. So here you see you have the RF signal. So the RF signal is attached to the electrodes. And here you have the signal once attached to the lower electrode. And then this is the RF signals, which will then be used to maintain the discharge. Then we can have a look to the results that we have at this particular pressure. And then we can control also the plasma homogeneity. DC self-gas voltage for the ion accelerations across the plasma sheath could also be taken into account. This is here, we are only consider here the plasma established into the plasma reactor. And we can compute here and analyze the whole behavior. And here we have a very good agreement with the literature. Especially, you can see how the plasma is then formed in the corner of this reactor, and you can also nicely see how automatically the sheath is also computed here in the simulation. Here you have another view, which is the isosurface value, which shows also the plasma distribution. So now if I'm plotting here along the z-axis, and I would like to identify here the effect of the ion density in this axis, in the z-axis, then we have these plots which is performed. So here you can also see something very important. We have a slight dissymmetric, which is in agreement with the transient analysis and with what has been published as well, because this is related depending at the time where we are also going to extract also these informations. What we nicely see here is the oscillation of the plasma here in this area. And then that's why also we see this dissymmetry. And now if we plot in the perpendicular direction, so in the y direction, if we plot now here the particle density, then we can also nicely see how the particle density is enhanced in close to the corner of the electrodes. And this is an effect which is also captured in this simulation. Let's now move on to the ICP reactor example. And here that's a complete analysis that I wanted to perform from structures that I've built from scratch in order to provide you with the workflow that we can consider and take it into account when we start from the geometry up to the simulation of the plasma regime. So let's start with the ICP reactors that you can see here on the screen. So this is a simplified structure in order to extract, as I said, best practice workflows. So the goal of these simulations is to characterize the main physical parameters, so RF and plasma formation, and also understand the main physical principles that we have out of this plasma reactor. And depending on the design, and everything can also be fully parameterized, we would like also to identify potential issues and damages, especially if you have the plasma which is hitting the walls and so on, creating also some potential damage that we can also analyze. And this can fully be performed doing some virtual prototyping. So this is the structure. So you have here the VHF coupler. Sometimes this is called an antenna. It's more a coupler because here there's no field propagation. The structure is very small compared to the wavelength. We are here just few couples of centimeter of size, working at 13.56 megahertz. We have a dielectric window in order to keep the plasma in this area, the plasma chamber, and the grounded electrode. So first of all, I'm doing the analysis without plasma. That means that I'm doing a kind of a cold analysis, an RF analysis, in order to identify how this plasma chamber behaves. Then you have, here I'm using the frequency domain solver, because as I said, the structures is very small compared to the wavelength. So that's very well suited, especially for resonance structure as well, that we are more using the frequency domain solvers in this context. So you see that if I'm starting directly from these simulations, taking into account the geometry as is, then we have here the response in terms of S parameters, which are then, we have a structures which is not matched at all. Then we need to design the so-called matching box for this kind of simulation. And this can be done via a 3D optimization process where we can directly add lumped elements, circuit elements, which then can be added whatever in the simulations directly in 3D, or it can be also computed directly within the circuit environment. And then you see here that we can tune here the matching box in order to get a matching response which is very well suited for the applications that we are interested in. Then we have here the response at 13.56 megahertz that we can fully control with the lamped elements that we have applied, whatever in the circuit simulations or in the 3D environment. And then we are starting now with the good initial conditions before introducing the discharge and creating the plasma. Let's now analyze the electromagnetic field distributions for the structures which is now well matched at 13.56 megahertz using our frequency domain solver. And then you see that we can then analyze the E-field distribution. The E-field distributions will be responsible of the discharge process, whereas the H-field distributions will be responsible for the species confinement. So in other words, we will create the plasma in this area, and the magnetic field will help in confining also this plasma in the area where we are interested about the etching process afterwards. So let's have a look now to the plasma formation. So we have here an input power which is introduced at 300 watt. That's important to get a matching structure already. So that means that the power that we are going to introduce from this area is really the power which will be transmitted to the area where we are going to create the plasma. We are using the argon neutral gas, and the pressure is defined here at 30 millitors. So as you've seen it also for the CCP reactor, you have here the argon neutral gas, which is then introduced with all here the information about the cross sections that you can enter. So this corresponds to the same plots that you've seen previously. And then here we can scale directly the electromagnetic field to an input power of 300 watts. So the external fields, which has been calculated with the frequency domain solvers, are now imported into the particle in cell simulation, which is here the electrostatic particle in cell simulation, and it needs to be scaled to the desired power that we would like to introduce into the device, which corresponds here to a 300 watt. And you can nicely see how the plasma is established. So this is the established regime that we have at the end, with the maximum density that we can also estimate. And you have here the ion density profile that we can have also out of the structure. And you can see here that we have a maximum density, which is also close to the corner, close to the edges of the grounded electrode, a bit in a similar way as we've seen it also for the CCP reactor. And this might create damages, and this is exactly what we need now to investigate. So the plasma formation, so then we have the ion density, we can plot the isosurface, and we see that we don't have exactly a perfect homogeneity of the plasma. So in other words, if we are going to analyze the electron energy, you see that the energy is enhanced and might create some potential damage close to the dielectric window here with the energy of the particles, which starts to be a little bit higher here. And of course, this is important to be analyzed because this might create damages. And this is not done here, but that would be also possible to couple this to any thermal analysis to see what is the effect on the increase of temperature in this area in order to find also the proper materials which has to be embedded into the device to get rid of any potential damages for the plasma reactor. And then we can use the results that we have obtained from the electrostatic peak solver to re-inject the parameters into the frequency domain solvers to analyze the detuning effect in the presence of the plasma. So you see the plasma physical parameters has then been extracted from the ESPEAK simulation. So typically we are able then to compute the plasma frequency. And then we are also able to compute the collision frequency, which acts here as a damping effect. So it introduces more losses into the plasma. So we use the Drude dispersion model, and all the parameters that you have here, the plasma frequency and the collision frequency, can then be entered with the parameters, which has then be extracted out from the ESP solver. Then we compute and we run once again the frequency domain solver. So this time we have the plasma which is established that we considered as a bulk using now a macroscopic approach. And you can see the new simulations taking into account the plasma that we have now a shift in frequency when we take into account the plasma. So we will need probably to reconsider also the tuning effect, the matching box with the lamped elements, which will have to be readjusted in order to maintain the frequency response at 13.56 megahertz. So this is something that we can fully control and fully estimate in order to design the plasma reactors for the applications we are interested in. So this brings me now to some summary and conclusions. So first of all, the benefits of using the simulations. You can really leverage the simulations here for your needs in performing plasma reactor simulation. So first of all, high fidelity modeling to predict and explain experimental results when you have no diagnostics available. And this is key. Of course, there are also probes and so on, which exist to also have some information, some diagnostics also for your plasma, but they are not all available also on demand. With the simulations, you can really access all the parameters that you are interested for your simulation. It reduced also cost by optimizing the device performance and with also a better reliability. And then, as you've seen, we can also predict potential damages also in this context. And this is key because you can predict in advance what needs to be the right design that you have to consider for the optimization of the plasma reactor. And then you can accelerate device validation and decision right directly after a virtual prototyping to validate the right plasma reactors that you would need for the semiconductor manufacturing processes you would like to consider. And then as a conclusion, we have, I think here, a unique value proposition. You can, with this approach, explore new plasma reactor designs, and we have a unique 3D plasma modeling. Plus the GPU support, you can really also reduce the simulation times. And I think this is key because you capture all the physical effects without any approximations. And we have this, and we have for this time domain approach and charged particle dynamics computations, which then can be taken into account in order to provide you with a complete solution. And you also have, you can also adapt or modify existing equipment to fulfill new requirements for new technologies. So you can have a design modification, and you can also consider any traceability. And this would be also the benefits of using the 3D experience platform when you have different models that you would like to modify, and then having all these effects that you can also store somewhere in order to validate at the end which design is best suited for my application. And you can also analyze and predict potential damages that you can also have in your device. And last but not least, then we have a complete technology with a large choice of solvers and meshing techniques that you can use. So for instance, there were one questions in the Q&A. So we don't have tetrahedral mesh with the PIC solver, because this is really efficient also to use it with the hex mesh and the GPU support. But the electrostatic PIC solvers, as well as the tracking solvers, is using both techniques, hexahedral mesh and tetrahedral mesh. And then we can also do a multiphysics approach with a potential thermal coupling analysis, which is also possible on demand. So that means that as soon as you have an increase of temperature into your device, you can couple this to a thermal analysis, and then you can really complete the loop and analyze the whole workflow for the design that you would like to perform and to analyze. With that, thank you very much for your attention, and I think we have a bit of time for some questions.